Imagine looking up at the night sky and seeing not just stars, but the echoes of cosmic explosions so powerful, they outshine entire galaxies for weeks. These are supernovas, nature's most spectacular fireworks, born from the violent deaths of massive stars. But here's something even more mind-blowing. Some of these explosions happened so far away, their light has traveled billions of years just to reach us, carrying secrets from the universe's earliest days. What if I told you that by studying these distant supernovas, scientists are rewriting the story of the cosmos itself? Think about this for a moment. Every time you gaze at a star, you're looking into the past. But the most distant supernovas take that idea to another level entirely. These are time capsules from an era when the universe was young, its galaxies still taking shape. They're not just flashes in the dark, they're messengers revealing how the universe expanded, how elements like gold and iron were forged, and even hinting at the mysterious force we call dark energy. Each one is a puzzle piece, helping us understand the grand tapestry of everything that exists. And that's exactly what we're diving into today. From the mind-bending distances these explosions span to the cutting-edge telescopes that capture their fading light, we're about to uncover 30 astonishing facts about the universe's most distant supernovas. You'll learn how astronomers spot these fleeting cosmic events, why they matter more than you might think, and what they tell us about the fate of the universe itself. So buckle up, we're about to embark on a journey across space and time, to the far edges of reality, where the universe's most violent and beautiful moments are waiting to be discovered. A supernova isn't just a star dying, it's a star going out with the biggest bang imaginable. Picture the most massive stars, those cosmic giants dozens of times heavier than our sun. When they run out of fuel, their cores collapse in a heartbeat, triggering an explosion so violent it rips the star apart. For a few glorious weeks, that single dying star can shine brighter than every other star in its galaxy combined. That's the raw power of a supernova, a cosmic firework so intense it's visible across the universe. But not all supernovas are created equal. Some, called Type 2, are the dramatic finales of those heavyweight stars we just talked about. They leave behind either a super-dense neutron star or, if the original star was truly monstrous, a black hole. Then there's Type 1a, a different kind of explosion entirely. These happen in binary star systems, where a tiny but incredibly dense white dwarf steals material from its companion until it reaches a critical mass, then boom. No remnant, just pure cosmic energy. What makes Type 1a special is their predictability. Because they always explode at the same brightness, astronomers use them like cosmic mile markers to measure distances across the universe. And here's the wild part, these explosions aren't just spectacular to watch. They're cosmic factories. The intense heat and pressure during a supernova forge heavy elements like gold, platinum, and uranium, then blast them across space. That means the ring on your finger or the phone in your hand likely contains atoms born in ancient stellar explosions. Without supernovas, those elements wouldn't exist, and neither would we. So the next time you look up at the night sky, remember, those fleeting flashes aren't just endings. They're also the reason anything complex, planets, life, even us, could exist at all. These cosmic explosions do more than just put on a dazzling light, show they're the ultimate recyclers of the universe. When a supernova erupts, it doesn't just vanish into the void. The shockwaves from these titanic blasts send newly forged elements hurtling through space at incredible speeds, scattering them across interstellar clouds like cosmic seeds. Over millions of years, those same clouds collapse under gravity to form new stars, planets, and eventually, the building blocks of life itself. Take iron, for example, the very same element that makes up Earth's core and flows through your blood. It wasn't created in the peaceful furnaces of ordinary stars. No, iron requires something far more violent, the unimaginable temperatures and pressures of a supernova explosion. In that split second when a massive star collapses, atoms are smashed together with such force that entirely new elements are born, and it's not just iron. Everything from the oxygen we breathe to the gold in our jewelry was once stardust flung across the cosmos by these explosive deaths, but the story gets even more remarkable. Without supernovas enriching the universe with heavy elements, rocky planets like Earth couldn't exist. Early in cosmic history, the universe contained only hydrogen and helium, the simplest elements. It took generation after generation of stars living, dying, and exploding to create the diversity of atoms we take for granted today. Our solar system formed from a cloud of gas and dust that had been polluted by countless supernovas over billions of years. In a very real sense, we are all made of recycled star debris, the legacy of explosions that happened long before our sun even ignited. This cosmic recycling has another fascinating twist. Different types of supernovas create different mixes of elements. Those massive stars that go out as Type II supernovas are responsible for most of the oxygen and magnesium in the universe. Meanwhile, the thermonuclear detonations of Type I supernovas produce huge amounts of iron and nickel. It's like nature has multiple factories, each specializing in different products, all working together to build the complex chemistry that makes life possible. And here's something that might make you look at the night sky differently. We can actually see this process happening right now. When astronomers analyze the light from distant supernovas, they can detect the chemical fingerprints of newly created elements in the expanding debris. Some of these elements will eventually become part of future planetary systems, continuing the cycle of stellar birth and death that's been shaping the universe for nearly 14 billion years. So the next time you feel insignificant under the vast night sky, remember, the atoms in your body were forged in the hearts of dying stars, scattered across the cosmos and assembled into something extraordinary. Measuring the distance to these cosmic explosions isn't as simple as stretching out a tape measure across the universe. Instead, astronomers rely on two extraordinary tools, the speed of light itself and a phenomenon called redshift. Let's start with light years, the universe's ultimate yardstick. 1 light year is the distance light travels in a single year, which works out to about 5.8 trillion miles. But here's where it gets mind-bending. When we observe a supernova 10 billion light years away, we're seeing it as it appeared 10 billion years ago because that's how long its light took to reach us. That flash in the sky isn't just a distant event, it's a time machine revealing the universe's past. Now, redshift takes this concept even further. Imagine an ambulance siren. As it moves away from you, the sound waves stretch out, lowering the pitch. Light behaves similarly. As the universe expands, it stretches the light traveling through space, shifting its wavelength toward the red end of the spectrum. The farther away a supernova is, the more its light gets stretched. By measuring exactly how much that light has redshifted, astronomers can calculate not just the distance to the explosion, but also how fast the universe was expanding at that moment in cosmic history. It's like peeling back layers of time, one color shift at a time. This technique revolutionized our understanding of the cosmos, especially when studying the most distant supernovas. In the late 1990s, astronomers made a shocking discovery: the universe isn't just expanding, it's accelerating. By comparing the redshift of faraway supernovas to closer ones, they realized these ancient explosions were dimmer than expected, meaning space itself was stretching faster over time. That finding, which earned a Nobel Prize, revealed the existence of dark energy, a mysterious force pushing galaxies apart. So every time scientists measure the light from a distant supernova, they're not just mapping space, they're decoding the very fabric of reality. What makes this even more remarkable is how precise these measurements have become. Modern telescopes like Hubble and JWST don't just detect redshift, they break light into detailed spectra, revealing the exact elements in the supernova's debris and confirming its distance with incredible accuracy. It's a cosmic game of connect the dots, where each explosion helps trace the universe's expansion history across billions of years. And as technology improves, we're peering even farther back, capturing supernovas from the universe's infancy, events so old, their light has been traveling for more than 90% of cosmic history. So the next time you hear about a distant supernova, remember, it's not just a number on a page. That measurement represents humanity's ingenuity in turning starlight into a roadmap of the cosmos, helping us unravel mysteries from the nature of dark energy to the ultimate fate of the universe itself. The hunt for the universe's most distant supernovas began with a single, groundbreaking discovery that changed astronomy forever. In the early 1990s, a team of scientists led by astronomer Mark Phillips made history by spotting a supernova so far away, its light had traveled 7 billion years to reach Earth. They weren't just seeing a star explode, they were peering back to a time when the Milky Way was still in its cosmic infancy. This revolutionary find wasn't luck. It depended on two game-changing tools: the Cerro Tololo Inter-American Observatory in Chile, with its 4-meter telescope capable of capturing extremely faint light, and a newly developed type of charge-coupled device, or CCD, that was 60 times more sensitive than previous detectors. Night after night, the team would photograph the same patch of sky, then use sophisticated software to compare new images with old ones, searching for any tiny speck of light that hadn't been there before. When they finally found their prize, designated supernova 1992 BG, it was like discovering a cosmic needle in a haystack the size of a galaxy. What made this discovery truly remarkable wasn't just the distance, but what it revealed about the early universe. The supernova's light showed surprising dimness, hinting that the expansion of space wasn't slowing down as most scientists expected. This tiny flicker from the distant past planted the first seeds of what would later become the dark energy revolution, the shocking realization that the universe's expansion is accelerating. Without those early observations, we might still be in the dark about one of cosmology's greatest mysteries. Today, the techniques pioneered by those astronomers have evolved dramatically. Where they once painstakingly compared photographic plates, modern surveys like the dark energy camera can scan entire galaxy clusters in a single night, automatically flagging potential supernovas within minutes. Yet every new distant supernova discovered still owes something to that first, faint flash of light captured 3 decades ago, proof that sometimes the most universe-shaking discoveries begin with a single point of light in the darkness. The current record holder for the most distant supernova ever observed goes by the unassuming name of DS16C2NM, a cosmic explosion so remote, its light began traveling toward us when the universe was just 1.6 billion years old. To put that staggering distance into perspective, this star died over 12.3 billion years ago, meaning its final moments unfolded when our Milky Way galaxy was barely formed. The light from that cataclysm spent more than 90% of the universe's lifetime crossing the cosmic void before finally reaching the dark energy camera in Chile in 2016. What makes DS16C2NM so special isn't just its mind-numbing distance, it's what the supernova represents. This wasn't one of the predictable Type 1 explosions scientists often use as cosmic measuring sticks. Instead, it was a rare Type 2 supernova, the violent death throes of a massive young star from the universe's formative years. Finding such an explosion at this extreme distance was like discovering a fossil from the first generation of stars, objects astrophysicists once thought we'd never observe directly. The supernova's light carried chemical signatures proving that even in those early epochs, stars were already producing heavy elements that would later seed future galaxies. Capturing this record-breaking event required both cutting-edge technology and perfect cosmic alignment. The Dark Energy Survey team was scanning vast swaths of sky when they noticed a faint, temporary glow near a distant galaxy cluster. Normally, finding such a dim speck would be impossible, But nature provided a helping hand. The immense gravity of the foreground galaxy cluster bent and magnified the supernova's light through an effect called gravitational lensing. This cosmic magnifying glass amplified the explosion's brightness by nearly 50 times, making the invisible suddenly visible. The implications of this discovery ripple across multiple fields of astronomy. By studying DS16C2NM's light curve and spectrum, scientists confirmed that massive stars in the early universe exploded differently than their modern counterparts. The pristine cosmic environment, back then lacking heavy elements, created hotter, more energetic blasts. This single data point is helping rewrite models of how the first stars lived and died, influencing everything from our understanding of early galaxy formation to the origins of elements essential for life. Perhaps most tantalizing is what this discovery suggests about future observations. With next-generation telescopes like the Vera-C, Rubin Observatory coming online, astronomers expect to find hundreds more of these primordial supernovas, each one offering another piece of the puzzle about how our universe grew from simplicity to complexity. DS16C2NM isn't just a record breaker. It's a preview of the cosmic revelations waiting at the edge of observable space. Supernovas don't just light up the cosmos, they serve as the universe's ultimate measuring tape. This incredible utility comes from a special class of explosions called Type 1 supernovas, often referred to as standard candles by astronomers. The term might sound poetic, but it's grounded in precise physics. These stellar explosions always reach the same peak brightness, giving scientists a cosmic reference point as reliable as a lighthouse beam cutting through fog. Here's why that consistency matters. Imagine you're standing in a dark field, looking at two identical light bulbs, one close, one far. The farther bulb appears dimmer, right? By comparing how bright a Type 1 supernova should be versus how dim it appears from Earth, astronomers can calculate its exact distance. It's like nature handed us a universal ruler with perfect calibration marks stretching back billions of light years. But these cosmic measuring sticks reveal far more than distance alone. When scientists mapped hundreds of distant Type 1 supernovas in the late 1990s, they noticed something bizarre. The most ancient explosions were slightly fainter than expected. This wasn't a measurement error. It was evidence that the universe's expansion rate had accelerated over time. That revelation, which turned cosmology upside down, led to the Nobel Prize-winning discovery of dark energy, the mysterious force pushing galaxies apart faster and faster. The precision of these measurements keeps improving. Modern surveys like the Pantheon Plus project combine data from over 1,500 supernovas, some so distant their light has traveled for over 10 billion years. By analyzing this vast sample, astronomers can now track how the universe's expansion speed has changed across nearly 80% of cosmic history. Each explosion is like a mile marker on an infinite highway, helping us reconstruct the universe's growth spurt from its fiery infancy to the present day. What makes supernovas truly indispensable is their versatility. Unlike other distance measuring techniques that work only at specific cosmic eras, these stellar explosions bridge the gap between nearby galaxies and the edge of the observable universe. They're the connective tissue in our cosmic map, linking observations of young, rapidly expanding space with measurements of our modern, accelerating cosmos. And with next-generation telescopes now scanning the skies, these standard candles are poised to reveal even deeper truths, perhaps even clues about whether dark energy's strength has changed over time, which could rewrite our understanding of the universe's ultimate fate. So the next time you hear about a distant supernova discovery, remember, that flash of light isn't just a spectacular cosmic event. It's a meticulously calibrated beacon helping humanity measure the immeasurable, one exploding star at a time. Before 1998, physicists were convinced they understood how the universe would end. a gradual slowdown, galaxies drifting apart ever more slowly as gravity pulled everything back together. Then came two teams of astronomers studying distant supernovas, and their findings shattered that assumption completely. What they discovered was so strange it required inventing a new term: dark energy, an invisible force pushing the universe apart faster and faster. The key evidence came from Type 1 supernovas, those reliable standard candles we discussed earlier. When scientists measured dozens of these explosions in faraway galaxies, they noticed something bizarre. The most distant supernovas, whose light had traveled billions of years to reach us, were significantly dimmer than predicted. This wasn't an equipment error or flawed calculations. The only explanation was that these ancient explosions were farther away than they should be, meaning the space between galaxies had stretched more than anyone anticipated. Imagine throwing a ball in the air, expecting it to slow down, only to watch it shoot upward like a rocket. That's essentially what the universe was doing. Dark energy wasn't just a tweak to existing theories, it upended them. Suddenly, the dominant force shaping the cosmos wasn't gravity's pull, but some mysterious repulsive pressure embedded in space itself. Here's how we know it exists. When astronomers compare supernovas from different cosmic eras, they can trace how the expansion rate has changed over time. Early in the universe's history, gravity briefly had the upper hand, slowing the expansion. But around 5 billion years ago, dark energy took over and the stretching of space began accelerating. Today, it accounts for nearly 70% of all the energy in the cosmos, silently dictating the universe's fate. What makes supernovas such perfect dark energy detectors isn't just their brightness, it's their distribution across cosmic time. By observing explosions from when the universe was half its current age, then comparing them to newer ones, astronomers essentially created a time-lapse of the cosmos expansion. The results were unambiguous. Space isn't just growing, it's growing faster every second, with galaxies racing away from each other at speeds that will eventually leave the night sky emptier and darker. This discovery raised more questions than answers. Is dark energy constant, or does its strength vary over time? Could it eventually tear atoms apart in a big rip? Supernovas are helping tackle these mysteries too. Recent surveys like the Dark Energy Survey have mapped thousands of explosions, searching for subtle patterns that might reveal whether dark energy's push has changed over billions of years. Each new data point brings us closer to understanding whether we're witnessing a temporary phase or the universe's irreversible destiny. Perhaps most astonishing is how humble tools, dying stars and their fading light, revealed something as profound as dark energy. Without supernovas acting as cosmic mile markers, we might still believe the universe was coasting to a gentle stop. Instead, we're left staring at a cosmos dominated by an invisible, unfamiliar force, its true nature still hidden in the darkness between galaxies. And it all started with a few strangely dim points of light in the night sky. Peering back to the universe's first few billion years, distant supernovas act like cosmic time capsules, each explosion preserving a snapshot of conditions when galaxies were young and space itself was far more crowded. These ancient stellar detonations reveal a world radically different from our modern cosmos. Back then, the universe was smaller, denser, and brimming with hot, newborn stars that lived fast and died violently. Supernovas from this era explode differently, burn hotter, and leave behind chemical signatures that tell the story of a cosmos still figuring out how to build complexity. Take the element oxygen, critical for life as we know it. Today's stars produce it gradually over millions of years, but in the early universe, massive stars forged oxygen in minutes during their explosive deaths. By analyzing the light from supernovas 12 billion light-years away, astronomers have detected surprising amounts of this element, proving that the first generations of stars worked at breakneck speed to seed the cosmos with heavy atoms. These measurements suggest that some early stars must have been colossal, up to 300 times the mass of our Sun, burning through their fuel so quickly that their entire life cycle from birth to supernova might have lasted just a few million years. The environment of these explosions was unlike anything we see today. Imagine a universe where galaxies were smaller but packed closer together, frequently colliding and triggering waves of star formation. In this cosmic pressure cooker, supernovas didn't just enrich their host galaxies, they blasted material into the thin intergalactic medium, creating vast filaments of gas that would later fuel new generations of stars. Some of these primordial explosions were so energetic, their shockwaves might have even helped shape the large-scale structure of the universe, nudging matter into the web-like patterns we observe today. Perhaps most astonishing is what these distant supernovas reveal about the laws of physics themselves. By comparing ancient explosions to modern ones, scientists have tested whether fundamental constants like the strength of gravity or nuclear forces have changed over cosmic time. So far, the verdict is clear. The physics governing a supernova 10 billion years ago matches what we observe today. This consistency across unimaginable timescales gives us confidence that the universe plays by the same rules everywhere, whether we're watching a star explode in a nearby galaxy or detecting the faint afterglow of a detonation that happened when Earth didn't even exist. Yet mysteries remain. Some ultra-distant supernovas appear to leave behind different remnants than their modern counterparts, suggesting early stars had unique compositions or explosion mechanisms we're still deciphering. Others seem embedded in galaxies that look nothing like our orderly Milky Way, chaotic, gas-rich systems where stars formed in frenzied bursts. Each new discovery peels back another layer, showing us a universe in its tumultuous youth, still experimenting with how to arrange matter and energy on the grandest scales. What makes this research so pivotal is its power to connect dots across cosmic history. When astronomers study these ancient explosions, they're not just examining individual stars, they're reconstructing the chain of events that turned a hot, featureless early universe into the diverse, element-rich cosmos we inhabit today. Every distant supernova is a data point in the universe's origin story, helping us understand how we went from a sea of hydrogen and helium to a world with planets, oceans, and life. And with next-generation telescopes now coming online, we're on the verge of discovering even older supernovas, perhaps some from the truly first generation of stars, whose death set the entire cosmic recycling process in motion. Spotting a supernova in our cosmic backyard is challenging enough, but hunting for explosions billions of light-years away pushes astronomy to its absolute limits. The light from these distant cataclysms is so faint by the time it reaches Earth, it's like trying to spot a single flickering candle on the moon through dense fog. Even with our most powerful telescopes, these ancient supernovas often appear as nothing more than a few extra pixels of brightness in a sea of galactic noise. Interference is another constant battle. Earth's atmosphere distorts and scatters light, which is why telescopes like Hubble and JWST had to be placed in space. But that's just the beginning. Distant supernovas often hide behind cosmic dust clouds or get lost in the glare of their host galaxies. Imagine trying to photograph a firefly next to a stadium floodlight from miles away. That's the scale of contrast astronomers are dealing with. And because these explosions fade quickly, sometimes in just weeks, there's no second chance. Miss the window, and that piece of cosmic history vanishes forever. This is where technology becomes a game changer. Hubble's razor-sharp vision has captured supernovas so remote, their light left when the universe was a quarter of its current age. But JWST takes it even further. Its infrared eyes peer through dust that would completely obscure visible light, revealing supernovas in regions of space we've never been able to explore before. These telescopes don't just take pretty pictures, they're time machines, collecting photons that have been traveling since the cosmos was in its infancy. Yet even with these technological marvels, discovery still depends on patience and luck. astronomers must stare at the same patch of sky for months, hoping to catch the brief moment when a distant star breathes its last. Advanced algorithms sift through terabytes of data nightly, flagging potential candidates among millions of stars. It's a cosmic version of finding a needle in a haystack, except the haystack is the size of the observable universe, and the needle only appears for a cosmic heartbeat before disappearing forever. What makes this painstaking work worthwhile is the payoff. Each distant supernova we manage to capture is like uncovering a single page from the universe's ancient diary, written in light and elemental ash. The challenges only heighten the significance when we finally detect one of these far-flung explosions. We're not just seeing a star's death, we're reclaiming a piece of cosmic history that would otherwise be lost to time and distance. Here's something that will bend your perception of reality when astronomers study the most distant supernovas. They're not just observing faraway events. They're literally looking back in time, watching stars die billions of years before Earth even existed. That flash of light you see in a telescope, it's not happening now. It's an echo from an era when the universe was young, a message written in photons that spent eons crossing the cosmic void just to reach our eyes. Think of it like receiving a letter with an ancient postmark. When we detect a supernova 12 billion light-years away, we're seeing it as it appeared 12 billion years ago, because that's how long its light took to travel to us. During all those millennia, while those photons were in transit, entire galaxies formed. Stars were born and died, and our solar system flickered into existence, but that light, carrying news of a stellar explosion, was already on its way, undisturbed by everything that happened afterward. This time travel effect isn't just poetic, it's a scientific goldmine. By cataloging supernovas at different distances, astronomers have assembled a cosmic flipbook showing how stars exploded across nearly the universe's entire history. The most distant ones reveal how early stars differed from modern ones. Some show evidence of being born from nearly pure hydrogen and helium, lacking the heavier elements that today's stars inherit from previous generations. Others suggest that massive stars in the early universe may have exploded differently, with more energy or unusual chemical signatures, because the physics of star formation worked differently in that primordial environment. What's truly mind-blowing is how this lets us test the consistency of physics itself. The light from ancient supernovas carries fingerprints of atomic interactions that happened billions of years ago. By comparing those signatures to modern experiments, scientists have confirmed that fundamental forces like electromagnetism and nuclear interactions haven't changed strength over cosmic time. That supernova you're seeing from halfway across the universe, its atoms behaved exactly the way ours do, proving the laws of physics are truly universal, both in space and across time. Yet there's a haunting twist to this cosmic time capsule. Many of the stars whose explosions we're just now witnessing likely left no descendants. Their host galaxies may have long since collided with others, their remains recycled into new stars that know nothing of their explosive origins. We're catching their final moments like flashes of lightning from a storm that ended before humanity existed. A fleeting glimpse of a vanished era, preserved only in light's relentless journey across an ever-expanding universe. This time delay effect means our view of cosmic history is permanently fragmented. Right now, light from even more ancient supernovas is en route to Earth but hasn't arrived yet. Somewhere out there, photons from the very first generation of stellar explosions are still traveling, destined to reach future telescopes billions of years from now. And conversely, civilizations in distant galaxies won't see our sun's eventual death for millions or billions of years. We're all prisoners of light speed, forever viewing the universe's story one delayed frame at a time, our cosmic cinema where the reels arrive eons after the projectors stopped running. At first glance, a supernova billions of light-years away might seem insignificant, a faint speck compared to the brilliant explosions in nearby galaxies. But here's the cosmic illusion at work. That dim glow isn't a sign of weakness. It's evidence of mind-bending distances and the relentless stretching of space itself. To understand why, picture two identical fireworks set off on a vast field, one close to you, the other at the far edge. The distant one appears smaller and dimmer, even though both release the same explosive energy. That's exactly what happens with supernovas across the universe. The numbers behind this are staggering. A typical Type 1 supernova, the kind used as cosmic mile markers, reaches an intrinsic brightness of about 5 billion times our sun's luminosity. Whether it explodes in our galactic neighborhood or the far reaches of the cosmos, that energy output remains the same. But by the time its light reaches Earth from extreme distances, its photons have spread across an expanding sphere of space so immense that only a tiny fraction strike our telescopes. Add to this the universe's expansion, stretching those photons' wavelengths, making them redder and sapping their visible energy, and you have a recipe for apparent dimness that has nothing to do with the explosion's actual power. This phenomenon becomes a goldmine for astronomers. By precisely measuring how much dimmer a distant supernova appears compared to nearby ones, scientists can calculate exactly how much space has stretched during the light's journey. It's like cosmic detective work, using brightness as a clue to reconstruct the universe's expansion history. Some supernovas from 7 billion light-years away appear 400 times fainter than their local counterparts, not because they were weaker explosions, but because the space between us and them has ballooned to unimaginable proportions during those billions of years of travel. What's truly fascinating is how this dimming isn't uniform. Supernovas from different cosmic eras fade in predictable patterns that reveal how the universe's expansion rate has changed over time. Those from 5 billion light-years away show less dimming than expected compared to their closer counterparts, evidence that dark energy's accelerating push only recently overcame gravity's pull. Meanwhile, the most distant supernovas exhibit extreme dimming not just from distance, but because their light spent most of its journey through a younger, denser universe where space expanded more slowly. Each measurement is like a time-stamped receipt showing how much the cosmos stretched during that light's voyage. This principle extends beyond supernovas to everything we observe in the distant universe. Quasars, gamma-ray bursts, even whole galaxies, all appear fainter not because they're less energetic, but because we're seeing them through the lens of an expanding spacetime continuum. The most powerful stellar explosions in the cosmos can be reduced to barely detectable flickers, their brilliance diluted across light years like a single drop of ink in an ocean. Yet hidden within that faint signal is all the raw power of a star's catastrophic end, encoded in photons that have witnessed the grand unfolding of cosmic history during their epic journey to our telescopes. So when astronomers point their instruments at these dim cosmic sparks, they're not seeing feeble remnants. They're witnessing titanic explosions filtered through the vastness of space and time, each photon a marathon runner completing a billion-year relay race to deliver its message about the universe's violent, brilliant past. The dimmer the light, the more extraordinary the journey it represents, and the more secrets it carries about how our cosmos grew from a dense fireball to the sweeping expanse we call home today. Even the most powerful telescopes have limits. Some supernovas are simply too far away to detect with current technology. That is, unless nature itself lends us a helping hand through gravitational lensing, one of Einstein's most astonishing cosmic predictions. Picture this: a supernova explodes 12 billion light-years away, its light too faint for any telescope to spot. But on its journey toward us, that light passes near a massive galaxy cluster. The cluster's immense gravity bends space-time like a funhouse mirror, curving the supernova's light around it and amplifying its brightness as if through a cosmic magnifying glass. Suddenly, what was invisible becomes detectable, all because gravity twisted the fabric of reality itself. This phenomenon isn't just theoretical. In 2014, astronomers witnessed a supernova nicknamed Redshift flicker to life 4 separate times around a galaxy cluster called MAX J1149.5 plus 2223. The cluster's gravity had split the supernova's light into multiple paths, each taking a slightly different route through warped space-time. Like staggered light beams through a prism, these images arrived at Earth months apart, offering a rare chance to study the same explosion from different angles. It was as if the universe had hit rewind and replay on a stellar death, giving scientists front-row seats to a cosmic encore. Gravitational lensing doesn't just magnify distant supernovas, it distorts them too. Some appear as stretched arcs or smeared crescents, their shapes warped by the uneven pull of dark matter within the lensing cluster. These distortions aren't flaws, they're clues. By mapping how the light bends, astronomers can weigh the invisible dark matter scaffolding the cluster, turning a supernova's glow into a tool for probing the universe's shadowy architecture. The most remarkable lensed supernovas become time machines in multiple ways. Take supernova Requiem, detected in 2021. Its light was lensed by a cluster so precisely that astronomers predicted it will reappear in roughly 16 years, as the light completes another loop around the cluster's gravitational well. This delayed replay lets us test cosmic expansion in real time, watching how the universe's stretching affects light's journey over decades. These cosmic mirages are rare. Only about 1 in every 20,000 supernovas gets significantly lensed, but new telescopes are tipping the odds. The upcoming Nancy Grace Roman Space Telescope will scan vast swaths of sky, hunting for these telltale brightening events. Each discovery promises a 2-for-1 deal, not just a glimpse of a dying star from the universe's youth, but also a free lesson in gravity's grip on the cosmos. So the next time you hear about an impossibly distant supernova, remember, sometimes the universe conspires to show us its secrets, bending the very rules of light and space to bring the farthest reaches of time within our view. A supernova's light is far more than just a brilliant flash. It's a cosmic barcode, containing precise information about the elements forged in that stellar explosion. When astronomers point their telescopes at these distant blasts, they don't just measure brightness. They break the light into its constituent colors using a technique called spectroscopy, revealing dark lines and bright bands that act like chemical fingerprints unique to each element. This is how we know distant supernovas are scattering iron, silicon, and oxygen across space, because their light carries the unmistakable signatures of these atoms. Here's how it works in practice. As light from an exploding star passes through its own expanding debris, atoms in that material absorb specific wavelengths, creating dark gaps in the spectrum. Each element leaves its own pattern, like musical notes missing from a song. Iron absorbs different wavelengths than oxygen, so by analyzing these gaps, scientists can reconstruct exactly what the dying star was made of and what new elements it created during its final moments. It's cosmic forensics, with light as the evidence and spectroscopy as the microscope. But these fingerprints do double duty. The same spectral lines also reveal how fast the supernova's debris is moving outward, because the element's absorption features shift toward the red end of the spectrum as they rush away from us, an effect called Doppler shift. Measure how much those lines have reddened, and you can calculate the expansion speed of the explosion itself. Combine that with observations of how quickly the light fades over weeks, and astronomers can distinguish between different types of supernovas even from billions of light years away. Perhaps most remarkably, spectroscopy lets us peer back in time to understand how early stars differed from modern ones. Supernovas from when the universe was young show cleaner chemical signatures, fewer heavy elements because they exploded before later generations of stars had polluted the cosmos. Some reveal strange patterns suggesting their progenitor stars formed from nearly pure hydrogen and helium, giving us direct evidence of the first stellar generations. It's like finding prehistoric ice cores, but written in light instead of layers. The precision of this technique keeps improving. Modern instruments like the James Webb Space Telescope's near-infrared spectrograph can detect elements present in mere trace amounts, revealing unexpected players like cobalt or even gold in supernova debris. Others track how these elemental signatures change day by day as the explosion evolves, showing elements forming in real time as the blast wave cools. What began centuries ago as simple prism experiments with sunlight has become our most powerful tool for decoding the universe's elemental recipe, one supernova spectrum at a time. So when you see those colorful graphs of squiggly lines in astronomy papers, remember, each dip and peak represents atoms created under the most extreme conditions nature can muster. They're not just data, they're the chemical birth certificates of elements that will one day form new stars, planets, and perhaps even life itself. And thanks to spectroscopy, we can read those certificates across billions of light years, uncovering the elemental alchemy that turns dying stars into the building blocks of everything we know. The brilliant flash of a supernova might seem instantaneous, but its light lingers far longer than most people realize. These cosmic explosions don't vanish like a camera flash. Instead, they fade gradually over weeks or even months, like embers cooling after a fireworks display. For nearby supernovas, this entire life cycle plays out in real time, with amateur astronomers tracking their slow dimming night after night. But when it comes to the most distant supernovas, we're often catching them months or years after their light first reached Earth, simply because their faint glow takes that long to rise above the background noise of the cosmos. Why such a dramatic difference? It all comes down to the physics of light and the vastness of space. A supernova's brightness follows a predictable curve. After the initial shockwave erupts, it reaches peak luminosity within days, then begins a steady decline as the expanding debris cools. For a relatively close explosion, say, in a galaxy 10 million light-years away, this entire process might be visible for several months before the light fades beyond detection. But for a supernova 10 billion light-years distant, the story changes completely. By the time its photons reach us, they've been stretched and diluted by the expansion of space itself, arriving as just a whisper of their original intensity. Catching these ultra-faint signals requires painstaking observation, often staring at the same patch of sky for weeks until that faint afterglow emerges from the cosmic static. This time delay creates a fascinating paradox. Some of the most distant supernovas we've discovered technically stopped shining billions of years ago. Their light has simply been traveling so long that we're only now witnessing what was once a fleeting event in the early universe. It's like hearing thunder minutes after lightning strikes, except scaled up to cosmic proportions. The Hubble Space Telescope's deep-field observations have captured supernovas that likely flared and faded before Earth existed, their light preserved in transit like insects trapped in amber. Modern surveys take advantage of this extended visibility window. Projects like the Dark Energy Survey don't just look for supernovas, they hunt for the telltale slow fade that distinguishes these explosions from other transient cosmic events. A distant supernova might first appear as a single faint pixel in an image, but if that pixel brightens over weeks before dimming again, astronomers know they've found something special. The most advanced telescopes can now track these changes in near real time, watching as light from a star that died 12 billion years ago waxes and wanes in our modern sky. What makes this extended visibility so valuable is the wealth of information hidden in the fading light. The rate at which a supernova dims reveals details about the explosion's energy and the elements it produced. Slower declines often indicate more nickel-56 was forged, a radioactive element that keeps the debris glowing longer as it decays. By comparing these light curves across cosmic distances, scientists have uncovered surprising consistencies in how stars died billions of years apart, proving the fundamental physics of stellar explosions hasn't changed even as the universe itself has transformed around them. Yet there's a bittersweet edge to these observations. Every distant supernova we detect is already long gone, its remnants scattered across space and recycled into new stars. We're not just watching light fade, we're witnessing the last echoes of events frozen in deep time. Their stories carried to us by photons that outlasted the very stars that created them. And with each new detection, we add another piece to the puzzle of how the universe's most violent moments shaped everything that followed. Those titanic shockwaves rippling outward from a supernova don't just destroy, they create. When a star explodes, it sends a supersonic blast wave tearing through interstellar space at millions of miles per hour, compressing nearby gas clouds with enough force to ignite stellar nurseries. It's nature's ultimate paradox. The same catastrophic event that ends one star's life can become the spark that lights dozens more. Picture a snowplow barreling through fresh powder, piling drifts higher and denser along its path. A supernova's shockwave works similarly, plowing through cosmic gas and dust with enough pressure to overcome the cloud's natural resistance to collapse. Computer simulations show these shock fronts can squeeze gas pockets thousands of times denser than their surroundings, precisely the conditions needed for gravity to take over and start forming protostars. Some of the most active star-forming regions we've observed, like the Orion Nebula, bear the chemical fingerprints of ancient supernovas, suggesting these explosions essentially seeded their own successors. The process isn't instant. After the initial blast, it might take 1 million years for those compressed gas clouds to fully collapse into baby stars. Yet the evidence linking supernovas to star birth is written across galaxies. Take the Large Magellanic Cloud. Astronomers have mapped young star clusters forming along the visible edges of supernova remnants, their ages matching exactly when the shockwave would have reached that location. It's as if the universe left us a cosmic paper trail connecting violent deaths to new beginnings. These triggered star births aren't subtle events. Some shockwaves carve out vast bubbles in interstellar gas, with new stars igniting along the expanding shell like fireworks bursting in slow motion. The most massive examples, called superbubbles, can stretch hundreds of light years across and host entire generations of stars, all sparked by a chain reaction of supernovas from a single stellar neighborhood. Our own solar system might owe its existence to such a phenomenon. Isotopic ratios in meteorites suggest a nearby supernova's shockwave could have jump-started the Sun's formation 4.5 billion years ago. But here's the twist: supernovas don't just encourage star formation, they regulate it. The same shockwaves that compress gas clouds also heat them, preventing runaway collapse that could overpopulate galaxies with stars. This delicate balance explains why some galaxies produce stars at a steady rate rather than in chaotic bursts. When a supernova explodes in a dense star-forming region, its blast can simultaneously trigger new stars while dispersing leftover gas, effectively pressing the cosmic reset button. The result is a self-regulating cycle where stellar deaths fuel and limit future births. The echoes of this process reach astonishing distances. In distant galaxies where we observe multiple supernovas occurring near gas-rich regions, telescopes like ALMA have detected telltale signs of compressed molecular clouds beginning their transformation into stars. These faraway examples show the same physics at work across cosmic time, proving supernova-triggered star formation isn't just a local phenomenon. It's a universal mechanism shaping galaxies from their earliest epochs to the present day. What makes this cycle truly remarkable is its longevity. The elements forged in each supernova become the raw material for the next stellar generation, meaning today's star-forming regions are cooking with ingredients recycled through countless explosions. That young star twinkling in a distant nebula, its chemistry carries the legacy of ancestors that died before Earth formed. And when those new stars eventually explode, they'll pass the baton again, a cosmic relay race where each fiery handoff builds ever more complex worlds. Spotting a supernova billions of light years away isn't just difficult, it's like winning the cosmic lottery. For every 1,000 supernovas astronomers detect in nearby galaxies, only a handful come from the distant early universe. The numbers tell the story. While modern surveys like the Zwicky Transient Facility catch around 10,000 supernovas each year, fewer than 1% of those represent explosions from when the universe was less than half its current age. And the truly ancient ones, those from the first few billion years after the Big Bang, we've identified barely 30 of those in 3 decades of searching. Several brutal realities make these discoveries so rare. First, there's the sheer distance. Light from these explosions dims exponentially as it crosses cosmic expanses, following the inverse square law. Move twice as far away and the light becomes 4 times fainter. By the time photons from a 12 billion-year-old supernova reach Earth, they've been diluted to a fraction of their original intensity, often drowned out by the glow of their host galaxies. Then there's time dilation's cruel trick. Because the universe was expanding rapidly during that light's journey, the supernova's brief flash gets stretched out, making it fade slower in our telescopes but also spreading its already meager light even thinner. Yet when astronomers do uncover one of these cosmic relics, the payoff is immense. Each distant supernova acts like a single frame in a stop-motion film of cosmic evolution, capturing physical conditions from an era we can't observe any other way. Take supernova UDS-10 Will, discovered in 2013. Its light traveled 12.2 billion years to reach us, making it the oldest Type 1 a supernova known at the time. When researchers analyzed its spectrum, they found surprising differences from modern examples, evidence that early white dwarf stars exploded differently when the universe was young. The scarcity also stems from observational limitations. Current telescopes can only scan so much sky with sufficient sensitivity, and supernovas are fleeting, visible for weeks or months before vanishing. Projects like the James Webb Space Telescope's Deep Field surveys dedicate hundreds of hours to staring at tiny patches of sky, hoping to catch a single distant explosion in progress. It's a waiting game where patience and luck collide, where years of effort might yield just one usable data point, but that single data point can rewrite textbooks. What makes each discovery invaluable is the unique window it provides into stellar chemistry's early days. Supernovas from the universe's first few billion years show cleaner elemental signatures, less polluted by generations of previous explosions, letting astronomers study star deaths in something approaching their primordial form. Some reveal unexpectedly high temperatures, suggesting early stars burned hotter and died more violently. Others hint at differences in how shockwaves propagated through the thinner interstellar medium of young galaxies. This rarity also forces creative solutions. When traditional surveys come up empty, astronomers turn to gravitational lensing, using galaxy clusters as natural telescopes to magnify faint, distant explosions. Projects like the Hubble Frontier Fields have leveraged this technique to spot supernovas otherwise beyond detection limits. Every outlier uncovered this way becomes a benchmark, helping refine models of how stars lived and died when the cosmos was fundamentally different. The hunt continues because these ultra-distant supernovas aren't just scientific curiosities, they're stress tests for our understanding of physics itself. Finding even one more from the universe's first billion years could reveal whether the earliest stars followed different rules, or whether constants like gravity's strength have drifted over cosmic time. In a field where answers often lead to deeper questions, each discovery shines light not just on dying stars, but on the origins of everything they helped create. The violence of a supernova explosion sends debris racing outward at unimaginable speeds. Even the most distant examples we observe still showcase this raw cosmic power. When a massive star collapses, the shockwave can accelerate stellar material to velocities exceeding 20,000 miles per second, fast enough to cross Earth's entire orbit in under an hour. Picture the kinetic energy of a bullet multiplied by billions, propelling fragments of a dead star so forcefully they outpace most spacecraft humanity has ever built. What's astonishing is how consistent these speeds remain across cosmic time. Supernovas from 12 billion years ago, when the universe was less than 2 billion years old, show debris expanding at nearly identical rates to modern explosions. This suggests the fundamental mechanics of stellar death haven't changed, even as the universe itself has evolved dramatically. Telescopes like JWST have captured spectra from these ancient blasts where the telltale Doppler shifts reveal sulfur and oxygen atoms fleeing the explosion site at 15,000 miles per second, their light stretched redder as they race away. These extreme velocities create two unique observational challenges. First, the debris field expands so rapidly that distant supernovas appear to evolve slower than nearby ones, an effect called cosmological time dilation. A supernova whose light took 10 billion years to reach us might seem to fade over months instead of weeks, its timeline stretched by the universe's expansion. Second, that same expansion means we're often catching these explosions mid-flight. By the time their light arrives, the debris has typically ballooned to a sphere dozens of light years across, making it impossible to resolve details even with our most powerful telescopes. Yet this expansion also leaves forensic evidence in the light itself. As the supernova's outer layers race outward, they thin and cool, causing specific elements to stop absorbing light at predictable points in the fading process. Astronomers use these transitions like a cosmic speedometer. The sooner a particular element's spectral signature disappears, the faster the material must be moving. Some hyper-distant supernovas show these changes occurring more gradually, suggesting their shockwaves encountered denser interstellar environments in the early universe's crowded galaxies. The speed of these explosions doesn't just affect how we observe them, it dictates their cosmic impact. Debris moving this fast can traverse entire galaxies within millennia, scattering heavy elements far from their birthplaces. When we detect iron or silicon in intergalactic space, it's often the residue of ancient supernovas whose material outtraced their home galaxy's gravity. These high-speed ejecta become the universe's long-haul freight trucks, distributing stellar ashes across voids where new stars may eventually form from the recycled wreckage. Perhaps most remarkably, these velocities help explain why we can see ultra-distant supernovas at all. The extreme kinetic energy converts to light when debris collides with surrounding gas, creating a sustained glow that lingers long after the initial flash. Without this prolonged afterglow fueled by the explosion's relentless speed, the light from these primordial explosions might have faded beyond detection before reaching our telescopes. So when we marvel at a supernova's brilliance across billions of light years, we're not just seeing a star's death, we're witnessing the enduring power of its final, universe-shaking sprint. Studying supernovas billions of light years away presents a challenge. Even with our most powerful telescopes, these explosions remain tiny pinpricks of light. That's where supercomputers step in, acting as cosmic laboratories where scientists can recreate these violent events down to the smallest detail. Picture a star collapsing at speeds approaching light itself, its core rebounding in a shockwave that rips the star apart. Simulating this requires more than just equations on a chalkboard. It demands processors performing quadrillions of calculations per second, tracking everything from nuclear reactions to the behavior of neutrinos streaming through the collapsing stellar core. One groundbreaking simulation, dubbed Chimera, recreated the final milliseconds of a massive star's life with unprecedented precision. Running on supercomputers at institutions like Oak Ridge National Laboratory, it revealed how shockwaves can stall during collapse, only to reignite when neutrinos deposit energy back into the star's outer layers. These insights solved a decades-old mystery about why some supernovas explode asymmetrically, ejecting material in jets rather than uniform spheres. Without such simulations, we'd have no way to test these theories, since observing the actual moment of collapse in distant stars remains impossible. What makes these digital recreations so valuable is their ability to explore what-if scenarios. Scientists can tweak variables like stellar mass, rotation speed, or magnetic field strength, then watch how each change alters the explosion. Some runs produce supernovas that fizzle out entirely, collapsing directly into black holes without a visible blast. Others generate hyper-energetic events matching the rare, superluminous supernovas observed in distant galaxies. By comparing thousands of simulations to real-world observations, astronomers can reverse engineer the physics governing stars too remote for direct study. The scale of these computations is staggering. A single simulation tracking just 1 second of stellar collapse might require 10 million CPU hours, equivalent to running 1,000 laptops continuously for over a year. Advanced visualization tools then transform these number-crunching marathons into stunning animations, showing shockwaves rippling through 3D stellar models in ways that reveal why certain elements get forged in specific layers. These visualizations aren't just pretty, they've exposed flaws in old theories, like how previous 2D models underestimated the role of turbulent eddies in reviving stalled shockwaves. Perhaps most remarkably, supercomputer simulations bridge the gap between distant supernovas and lab experiments here on Earth. Facilities like the National Ignition Facility use lasers to recreate microsecond-scale slices of supernova conditions, generating data that helps refine the digital models. It's a virtuous cycle. Each iteration makes the simulations more accurate, letting astronomers decode fainter signals from real supernovas. So when telescopes like JWST spot a dim explosion near the edge of the observable universe, supercomputers can unpack its story, revealing details about a star we'll never see directly, all from the echo of its death throws across billions of years. What started as theoretical guesswork has blossomed into one of astrophysics' most powerful tools. Those fleeting flashes captured by telescopes are no longer just points of light. Thanks to supercomputers, they've become open books, their pages filled with secrets about how stars live, die, and sculpt the universe around them. And with each technological leap, these digital cosmic laboratories peel back another layer, turning the most distant supernovas from enigmatic blips into rich sources of discovery. Some of the universe's most distant supernovas hide an even more explosive secret. They're linked to gamma-ray bursts, the brightest electromagnetic events known to science. These aren't your average stellar explosions. We're talking about beams of energy so intense they can outshine entire galaxies for seconds, releasing more power than our sun will emit in its entire 10 billion-year lifetime. The connection between these two cosmic phenomena wasn't obvious at first. For decades, gamma-ray bursts were mysterious flashes detected by military satellites during the Cold War, their origins debated as everything from nuclear tests to alien signals. It wasn't until the late 1990s that astronomers noticed something remarkable. Some bursts left behind fading afterglows that looked suspiciously like supernovas. The breakthrough came with gamma-ray burst 990712 and its optical counterpart, Supernova 1998 BW. For the first time, scientists had concrete proof that at least some bursts coincided with the deaths of massive stars. Here's how it works. When certain extremely massive, rapidly rotating stars collapse, they don't just explode outward evenly. Instead, the star's core forms a black hole, and the remaining material gets funneled into twin jets moving at nearly light speed. These jets, narrower than a pencil beam relative to their length, punch through the dying star's outer layers. If one happens to be pointed at Earth, we detect it as a gamma-ray burst, a blinding flash of high-energy radiation. The wider, slower explosion we see afterward, that's the conventional supernova. The star remains expanding in all directions. Detecting these linked events across cosmic distances requires perfect timing and coordination. Gamma-ray telescopes like NASA's Swift satellite catch the initial burst, often lasting just milliseconds to minutes. Ground-based telescopes then scramble to pinpoint the location before the afterglow fades, sometimes within hours. For the most distant examples, like gamma-ray burst 080913 at 12.8 billion light-years away, catching the subsequent supernova meant weeks of observations with Hubble and other space telescopes to distinguish its light from the host galaxy's glow. What they found rewrote our understanding of stellar death. These weren't normal supernovas, but hypernovas, up to 100 times more energetic, their unusual spectral signatures revealing exotic physics at work. The implications stretch far beyond classification. Gamma-ray bursts accompanying supernovas act like cosmic lighthouses, their brilliant flashes making visible galaxies that would otherwise be too dim to study. When burst 060218 went off in 2006, its afterglow illuminated a galaxy just 900 million years after the Big Bang, a time when the first stars were still forming. The supernova's spectrum showed surprisingly high levels of nickel-56, suggesting early stars could produce heavy elements much faster than models predicted. Without the gamma-ray burst's beacon drawing attention, we might never have spotted this crucial data point about the universe's chemical evolution. Yet for all their brilliance, these events remain extraordinarily rare. Only about 1% of supernovas generate gamma-ray bursts visible from Earth. The jets have to be aligned almost perfectly with our line of sight. Simulations suggest the progenitor stars must be massive, low in heavy elements, and spinning rapidly to form the required accretion disk around the newborn black hole. Finding such a combination in the early universe, where stars tended to rotate faster and lacked heavy elements, might explain why the most distant bursts seem different from nearby ones. Some show unusual light curves suggesting their jets drilled through thinner stellar envelopes, or that magnetic fields played unexpected roles in focusing the energy. What makes these dual explosions truly invaluable is how they bridge cosmic scales. The gamma-ray burst gives us an ultra-precise timestamp and direction, while the supernova provides chemical details about the parent star. Together, they form a complete picture of stellar death impossible to glean from either phenomenon alone. As telescopes grow more sensitive, astronomers hope to catch even earlier examples, perhaps from the universe's first generation of stars, whose deaths may have followed entirely different rules. Every new detection adds another piece to the puzzle of how the most violent events in nature shape the cosmos we see today. The next decade promises a revolution in our understanding of distant supernovas, thanks to a new generation of telescopes designed to push the boundaries of cosmic exploration. Leading this charge is the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s with capabilities that will make Hubble's deepest observations look like snapshots of our cosmic backyard. Unlike traditional telescopes that study small patches of sky in detail, Roman will feature a field of view 100 times larger than Hubble's infrared camera, allowing it to scan vast swaths of the universe in a single sweep. This means it could discover thousands of supernovas annually, including rare, ultra-distant examples from the universe's first billion years that have eluded detection until now. Roman's secret weapon lies in its infrared sensitivity. As supernova light travels across expanding space, its wavelength stretches into the infrared spectrum, making these ancient explosions virtually invisible to optical telescopes. Roman's specialized instruments will cut through this cosmic haze, revealing supernovas so far away, their light has been traveling for over 90% of the universe's history. Even more remarkably, the telescope will monitor the same sky regions repeatedly, catching supernovas at different stages of their life cycles, from initial shock breakout to gradual fading. This time-lapse view could finally answer long-standing questions about whether the earliest stars exploded differently than their modern counterparts. But Roman won't be working alone. The Vera C. Rubin Observatory's legacy survey of space and time will complement these efforts by scanning the entire southern sky every few nights with its 3.2 billion pixel camera. While less sensitive to the most distant supernovas, Rubin's sheer volume of data will help identify transient events for follow-up by other telescopes. Together, these missions will create a dynamic map of stellar explosions across cosmic time, revealing patterns in how supernova rates have changed as galaxies evolve. Beyond these giants, specialized missions are taking supernova research in bold new directions. The European Space Agency's Euclid spacecraft is already mapping the distribution of dark matter using gravitational lensing, a technique that could serendipitously magnify distant supernovas otherwise too faint to study. NASA's upcoming SPHEREX mission will conduct an all-sky infrared survey that might uncover supernovas hidden in dusty galactic regions. And on the ground, the extremely large telescope's 39-meter mirror will dissect the chemical fingerprints of ultra-distant supernovas with unprecedented precision when it sees first light in 2028. Perhaps most exciting are the unexpected discoveries these tools might enable. Just as Hubble's deep fields revealed galaxies where none were predicted to exist, Roman and its successors could uncover entirely new classes of stellar explosions from the universe's dawn. Some theorists speculate we might find pair instability, supernovas' hypothetical giga-explosions of the first stars, so powerful they leave no remnant behind. Others predict a trove of superluminous supernovas fueled by exotic physics possible only in the pristine early cosmos. The data deluge from these missions will demand equally advanced analysis tools. Machine learning algorithms are being trained to sift through millions of cosmic detections, flagging the rarest supernovas in real time. Future citizen science projects might enlist amateur astronomers worldwide to help classify these events, much like earlier projects revolutionized galaxy mapping. What emerges will be more than just a catalogue of explosions. It will be a chronicle of how stars have lived, died, and reshaped the universe from its fiery beginnings to the present day. This isn't just about breaking distance records. Each new supernova discovered at the edge of observable space offers a fresh test of cosmological models, from the nature of dark energy to the universality of physical laws. With these telescopes as our time machines, we're poised to witness stellar deaths that occurred before the Milky Way took its modern form, explosions whose light has been racing toward us since the cosmos was young, carrying answers to questions we're only beginning to ask. Humanity's fascination with supernovas stretches back thousands of years, long before we understood their true cosmic nature. Ancient Chinese astronomers left some of the most meticulous records, documenting a brilliant guest star in the year 1054 that shone so brightly it was visible for weeks even in daylight. We now know they were witnessing the Crab Nebula's birth, a supernova remnant still expanding today. Halfway across the world, ancestral Pueblones in what's now New Mexico may have captured that same event in a petroglyph showing a crescent moon beside a radiant circle, proof that these explosions seared themselves into human consciousness long before telescopes existed. This cultural imprint only grew with time. Renaissance artists subtly wove the supernova of 1572, observed by Tycho Brahe, into their works as celestial omens. Shakespeare's plays contain references to blazing stars that scholars link to these awe-inspiring events. Fast forward to the modern era, and supernovas have become narrative powerhouses in science fiction, from Arthur C. Clarke's The Star to Marvel's Eternals, where an impending supernova serves as both apocalyptic threat and cosmic rebirth metaphor. Their sheer scale makes them irresistible storytelling devices, cataclysms that reshape worlds yet also seed them with the elements for new beginnings. What's remarkable is how this cultural footprint extends even to supernovas we've never directly witnessed. The concept of stars dying violently in distant galaxies has inspired musicians like Björk in her album, Biophilia, where she composed a song based on supernova light curves. Video games like Mass Effect feature entire alien civilizations harnessing energy from artificial supernovas. These creative interpretations reflect a profound truth. Whether observed through ancient eyes or modern telescopes, supernovas represent the universe's dramatic cycles of destruction and creation made visible. Perhaps most unexpectedly, ultra-distant supernovas now influence contemporary art installations. Artist Rafik Anadol's Machine Hallucinations series uses real astronomical data, including light curves from galaxies billions of light-years away, to generate immersive digital experiences. Viewers walk through swirling visualizations of supernova remnants they'll never see through a telescope, connecting with cosmic events that occurred before Earth formed. It's a full-circle moment where cutting-edge science and human creativity collide, proving these stellar explosions still captivate us just as powerfully as they did our ancestors staring at the night sky millennia ago. The enduring legacy of supernovas in culture reveals something fundamental about humanity. Whether carved in stone, written in verse, or rendered in pixels, we keep returning to these cosmic explosions as mirrors reflecting our own fears of annihilation, hopes for renewal, and relentless curiosity about our place in the universe. And as telescopes uncover ever more distant examples, this cultural dialogue only deepens, linking the primal wonder of ancient skywatchers to the quantum precision of modern astrophysics in one unbroken chain of awe. The stars that explode as distant supernovas hide their identities well despite decades of searching. Astronomers still can't pin down exactly what kinds of stellar ancestors produce certain cosmic explosions we spot near the edge of the observable universe. It's like investigating a crime scene billions of years after the fact where the culprit has vanished into the cosmos, leaving only fleeting chemical clues in the debris. For nearby supernovas, we often spot the progenitor star in pre-explosion images, but for those ultra-distant bursts of light, tracing them back to their origins requires piecing together evidence from their afterglow like cosmic forensics. Take superluminous supernovas, these mysterious hyper-bright explosions, sometimes 100 times more powerful than ordinary supernovas, keep defying expectations. Some last for months rather than weeks, glowing far longer than physics models predict. Others show bizarre chemical compositions with unexpected amounts of elements like calcium or titanium. The leading theory suggests they might come from magnetized neutron stars with unimaginably strong magnetic fields that inject extra energy into the explosion. But competing ideas propose collisions between white dwarfs in dense star clusters, or even the explosive deaths of stars 200 times more massive than our Sun. The truth, we've caught these spectacular blasts in action across billions of light years, but their birth stories remain hotly debated. The challenge grows more complex when we look back to the universe's first few billion years. Stars in that era formed from nearly pure hydrogen and helium, lacking the heavier elements that influence how modern stars live and die. Computer simulations suggest these pristine progenitors might have burned hotter, exploded differently, or even collapsed directly into black holes without a visible supernova at all. Some distant explosions show light curves that don't match any known local supernovas, hinting at stellar physics operating under rules we haven't fully deciphered. It's like finding dinosaur bones that don't fit any known species, proof that the early universe hosted stellar beasts unlike anything in our cosmic neighborhood today. Gravitational lensing offers unexpected help in this detective work. When a massive galaxy cluster bends and magnifies light from a faraway supernova, it occasionally provides enough detail to spot the host galaxy, a crucial clue about the progenitor's environment. One lensed supernova from 11 billion years ago appeared in a tiny, chaotic galaxy bursting with young stars, suggesting its progenitor was a short-lived blue giant rather than an aged red supergiant. Other lensed examples emerge from galaxies rich in gas but poor in metals, conditions that might produce unstable, rapidly rotating stars prone to violent deaths. The James Webb Space Telescope is now turning these theoretical musings into concrete data. Its infrared eyes have begun capturing spectra of supernovas so distant, their progenitor stars existed when the universe was less than 2 billion years old. Early results reveal surprising amounts of carbon and oxygen in some explosions, elements that shouldn't be so abundant unless the original star had an unusual structure or explosive mechanism. Every new observation chips away at the mystery, proving that the stars of the ancient cosmos played by different rules, dying in ways that still challenge our understanding of stellar life cycles. What makes this search so vital isn't just scientific curiosity. It's about decoding the universe's instruction manual for star death. Each unidentified progenitor represents a gap in our knowledge of how the earliest stars seeded the cosmos with heavy elements. Some might belong to entirely new categories of stellar objects that no longer exist in today's universe, their unique physics lost to time. Others could reveal why certain galaxies from cosmic dawn appear chemically enriched earlier than models predict. Until we solve these puzzles, our map of stellar evolution remains frustratingly incomplete, missing the very chapters that explain how the universe transformed from simplicity to the rich chemical diversity we see today. For now, these mystery progenitors linger at the edge of discovery, their existence confirmed by brilliant explosions across the ages, their true natures still hidden in the darkness of deep time. Every strange light curve, every anomalous chemical signature is a whisper from the past, challenging us to listen more closely to the stories stars tell when they die. And with each new generation of telescopes, we get one step closer to deciphering these cosmic last wills and testaments, written not on paper but in the elemental ashes scattered across the universe. You might think discovering a supernova billions of light years away requires billion-dollar telescopes and teams of PhDs, but sometimes all it takes is a backyard telescope and sharp-eyed persistence. Amateur astronomers have repeatedly played crucial roles in spotting these cosmic explosions, proving you don't need NASA-level gear to contribute to cutting-edge science. Take the story of 10-year-old Catherine Gray from Canada, who in 2011 became the youngest person ever to discover a supernova, a Type 1a explosion in the galaxy UGC 3378, roughly 240 million light-years distant. Using images from her astronomer father's telescope and software that compares newer observations with archival shots, she noticed a tiny speck of light where none existed before, joining the ranks of citizen scientists who have expanded our map of stellar explosions. What makes these contributions so valuable isn't just the thrill of discovery, it's volume. Professional telescopes can't monitor every galaxy continuously, leaving gaps where fleeting supernovas might blink in and out of existence unnoticed. That's where distributed projects like the All-Sky Automated Survey for Supernovas, or ASAS-SN, come in. With telescopes stationed across the globe and data accessible to volunteers worldwide, this network has uncovered hundreds of supernovas, including some from the universe's distant reaches. In 2018, amateurs sifting through ASAS-SN data spotted a supernova nicknamed the Cow. An unusually bright and rapid explosion later confirmed to be a rare stellar tidal disruption event halfway across the observable universe. The tools available to citizen scientists keep evolving. Platforms like Zooniverse's Supernova Hunters let anyone with an internet connection scour telescope images for telltale bright spots, with volunteers collectively analyzing millions of galaxy snapshots. Some particularly eagle-eyed participants have flagged anomalies that algorithms missed, like the faint glow of a supernova partially obscured by its host galaxy's dust. Other initiatives target specific challenges. The Backyard Worlds Planet 9 project, while primarily hunting nearby cosmic objects, has serendipitously found supernovas in distant galaxies because participants noticed subtle changes professional surveys overlooked. There's also an art to distinguishing true supernovas from imposters. amateurs learn to rule out asteroids, variable stars, and even camera artifacts by checking multiple observations over time. Some develop such expertise they can estimate a supernova's type just from its light curve's shape, skills honed through years of comparing notes in online forums like the American Association of Variable Star Observers. This grassroots knowledge sharing creates a ripple effect. When one volunteer spots something unusual, global networks can quickly mobilize professional telescopes for follow-up, turning a single observation into publishable research. Perhaps most remarkably, these discoveries aren't just statistical flukes, they're reshaping our understanding of cosmic diversity. In 2020, a Japanese amateur astronomer detected a supernova in the galaxy M61 that defied classification, exhibiting a bizarre mix of hydrogen-rich and hydrogen-poor spectral features. Professional follow-up revealed it was a Type 2L supernova, a rare subtype providing clues about how massive stars shed their outer layers before exploding. Without that initial amateur alert, this vital data point might have vanished before anyone noticed, the next frontier for citizen supernova hunters. Real-time alerts from next-generation surveys like the Vera-C Rubin Observatory, which will flood amateur networks with potential candidates faster than ever. Early tests show volunteers can triage these alerts with over 90% accuracy, freeing professional astronomers to focus on the most scientifically valuable targets. In an era where telescopes generate more data than any research team could analyze alone, these distributed efforts aren't just helpful, they're essential for catching the rarest, most distant explosions that might otherwise slip through the cracks. So while headlines often focus on billion-dollar instruments, remember, some of the universe's most profound secrets are still being uncovered by passionate stargazers in their backyards, one pixel of light at a time. The violent death of a star may seem silent from our vantage point, but hidden within the light of distant supernovas is a symphony waiting to be heard. Astronomers have pioneered a remarkable technique called sonification, translating the flickering light curves and spectral data of these cosmic explosions into audible soundscapes. Picture the rising and falling brightness of a supernova stretched across time, with each fluctuation mapped to a musical note. The result isn't just scientific data, it's the universe's most powerful explosions reinterpreted as otherworldly melodies. This process works by assigning specific tones to different wavelengths of light. When a supernova's spectrum reveals elements like iron or silicon through their absorption lines, those chemical fingerprints become distinct musical pitches. The Doppler shift, that telltale stretching of light as debris races outward, manifests as a descending tone, like a cosmic sigh fading into the void. Some teams even layer multiple elements together, creating harmonies from the very atoms forged in the explosion. The most distant supernovas produce eerily deep tones due to their extreme redshift. Their light waves stretched so far they translate into bass frequencies that vibrate right through you. One of the most haunting examples comes from supernova 1987, the closest stellar explosion observed in modern times. Scientists at NASA's Chandra X-ray Observatory converted its light curve into a shimmering cascade of notes, where the initial violent spike becomes a sudden crescendo before fading into a lingering drone. More distant examples sound fundamentally different. A supernova 10 billion light-years away might produce a slow, drawn-out tone that reflects how the expansion of space has stretched both its light and its timeline. Beyond artistic appeal, sonification offers real scientific value. The human ear can detect subtle patterns in data that might elude visual analysis, like irregularities in a light curve's decline that suggest unusual amounts of radioactive nickel. Some researchers have spotted previously unnoticed echoes in supernova remnants by listening to multi-wavelength data as overlapping tones. It's a powerful reminder that science isn't just about seeing. Sometimes, hearing cosmic phenomena reveals secrets hidden in plain sight. The emotional impact of these sounds shouldn't be underestimated either. There's something profoundly moving about experiencing a star's death not as abstract data points, but as a visceral vibration you can feel in your bones. Composers have begun incorporating these celestial soundscapes into orchestral works, blending the universe's raw acoustics with human creativity. The resulting pieces bridge billions of years and light years, connecting us to events so distant and ancient they defy comprehension, yet suddenly feel immediate through the universal language of sound. Perhaps most remarkably, this technique works for the faintest supernovas too. Even when the light from an explosion 12 billion light-years away registers as just a few pixels on a detector, its redshifted wavelengths can still be translated into a whisper-thin tone, a ghostly echo from the universe's youth that we can finally hear alongside seeing. These sonic time capsules prove that the cosmos doesn't just speak to us through light, but through rhythms and vibrations waiting to be decoded by anyone willing to listen. Not all stellar deaths are created equal. While some supernovas leave behind dense neutron stars, others collapse into far more mysterious objects, black holes. When particularly massive stars explode in distant galaxies, their cores don't just stop collapsing at neutron star density. Instead, they continue imploding until gravity becomes so overwhelming that not even light can escape, birthing a singularity shrouded in an event horizon. These cosmic vacuum cleaners start their lives hidden behind the brilliant veil of a supernova's outer layers, only revealing their true nature once the stellar debris clears. Studying distant supernovas gives us a unique window into black hole formation's early history. Cosmologists suspect the first black holes formed from population 3 stars, hypothetical giants hundreds of times more massive than our Sun, that existed in the universe's first few 100 million years. When these behemoths exploded as supernovas, their cores likely collapsed directly into black holes without passing through a neutron star phase. Telescopes like JWST are now searching for telltale signs of these direct collapse events in supernovas near the cosmic dawn. Some show unusual light curves, explosions that brighten quickly but fade slowly, hinting at black holes swallowing inner debris before it can contribute to the visible afterglow. The physics behind this transformation is mind-bending. During a supernova's collapse, if the remaining core weighs more than about 3 solar masses, quantum forces can no longer resist gravity's pull. Matter gets compressed beyond comprehension, a star's entire mass crushed into a space smaller than Manhattan. We can't observe this process directly, but distant supernovas provide crucial clues through their explosive aftermath. Some exhibit asymmetric jets of material blasted outward at near light speed, suggesting the newborn black hole's intense rotation flung debris in specific directions. Others show abrupt drops in brightness as portions of the collapsing star get swallowed by the emerging event horizon mid-explosion. What makes these observations invaluable is how they reveal black holes' diversity. Supernova remnants in nearby galaxies have helped identify stellar mass black holes weighing 5 to 50 suns, but the most distant examples might explain the origins of far larger monsters, intermediate mass black holes with hundreds or thousands of solar masses. A few ultra-distant supernovas show energy outputs suggesting their collapsed cores were unusually massive from birth, possibly because their parent stars formed in the metal-poor early universe where stars could grow bigger. These could represent missing links between small stellar black holes and the supermassive behemoths lurking in galaxy centers today. Perhaps most intriguing are the failed supernova stars that seem to vanish without the expected brilliant explosion. Astronomers have spotted several cases where a massive star brightens slightly, then disappears from view entirely. The leading theory: these stars collapsed directly into black holes so efficiently that most of their material fell inward rather than exploding outward. Finding such events in distant galaxies would confirm that black holes can form through multiple pathways, not just violent supernovas. Every distant supernova we catch in the act of birthing a black hole adds another piece to this cosmic puzzle. From the peculiar light curves betraying a newborn singularity's appetite, to the elemental signatures revealing how much material avoided being swallowed, these observations help us understand one of nature's most extreme transformations, where a dying star's final act isn't just an ending, but the creation of something even more enigmatic. And with gravitational wave detectors now complementing traditional telescopes, we're closer than ever to witnessing black holes' violent births across cosmic time. Buried in the light from some of the universe's most distant galaxies lies forensic evidence of supernovas so ancient, their explosions predate Earth's formation by billions of years. These aren't the billowing nebulas we see in nearby space like the Crab or Cassiopeia, they're ghosts of explosions so old, their visible remnants have long since dissipated into the interstellar medium. Yet through ingenious detective work, astronomers have identified chemical fingerprints of these primordial blasts in the atmospheres of stars from our own Milky Way. Imagine finding ash particles from a campfire that burned before human civilization began. That's the scale of cosmic archaeology we're talking about here. One remarkable example comes from a star catalogued as E1523-0901, located in our galaxy's halo. Spectroscopic analysis revealed it contains absurdly high levels of elements like strontium and europium, a chemical cocktail only possible if the star formed from gas enriched by multiple supernovas from the universe's first stellar generation. The timing is staggering. This star's material carries traces of explosions that occurred perhaps just 100 million years after the Big Bang, when the cosmos was still in its infancy. What's astonishing isn't just the age, but what these remnants tell us about early star deaths. The elemental ratios match predictions for pair instability, supernovas, hypothetical hyper-explosions of stars 250 times more massive than our Sun, so powerful they completely obliterate themselves without leaving neutron stars or black holes behind. But supernova remnants from the cosmic dawn aren't just preserved in stellar atmospheres. Some reveal themselves through subtle distortions in the cosmic microwave background, the afterglow of the Big Bang itself. When the first massive stars exploded, their intense ultraviolet radiation reionized neutral hydrogen throughout the early universe, leaving faint polarization patterns in the microwave background that satellites like Planck have detected. These aren't traditional remnants we can image, but rather the lasting imprint of supernova-driven changes to the cosmos' very structure. It's as if the explosions left shadows on the fabric of space-time, visible only through their influence on the universe's oldest light. Distant galaxy observations add another layer to this detective story. Quasars, extremely luminous active galaxies, sometimes show absorption lines in their spectra caused by intervening gas clouds. Some of these clouds exhibit iron to hydrogen ratios 10,000 times higher than the Sun's, yet exist in regions nearly as old as the universe itself. The only plausible explanation: these are the dispersed remnants of countless early supernovas, their heavy elements drifting through intergalactic space for billions of years. Unlike the beautiful nebulas we photograph in nearby space, these remnants are more like cosmic smoke, invisible individually but detectable through their cumulative pollution of pristine intergalactic gas. The James Webb Space Telescope has begun revealing even more direct evidence. Its infrared eyes have spotted distant galaxies exhibiting unusual brightness fluctuations that suggest recent supernova activity, while their spectra show broad emission features characteristic of expanding shock waves from ancient explosions. One galaxy observed at redshift 8 when the universe was just 650 million years old shows silicon and oxygen emission lines extending thousands of kilometers per second, clear signatures of supernova-driven winds. These aren't the neatly defined shells we see in local remnants, but rather the chaotic aftermath of explosions occurring in galaxies still taking shape, where supernovas were far more frequent and violent than today. What makes these primordial remnants so scientifically precious is how they capture stellar physics operating under fundamentally different rules. Without heavy elements to cool collapsing gas clouds, the first stars formed from nearly pure hydrogen and helium, leading to hotter, more massive stellar objects that lived fast and died young. Their supernova remnants tell stories of explosions 10 times more energetic than anything in today's universe, enriching their surroundings with unique elemental mixes. Some theoretical models suggest the very first supernovas may have produced entirely different sets of elements compared to modern counterparts, possibly including unusual isotopes that no longer exist naturally. These time capsules also help solve cosmic mysteries. The dispersion patterns of ancient supernova remnants provide clues about how galaxies first retained or lost their gas, a process crucial for understanding why some galaxies stopped forming stars billions of years ago. Their metal distributions challenge assumptions about how quickly the universe transitioned from pristine simplicity to chemical complexity. And by comparing predicted versus observed remnant signatures, cosmologists can test theories about the early universe's density fluctuations that seeded all later structure. Perhaps most remarkably, some of these remnants might still be visible indirectly through their influence on later generations. The Fermi bubble's gigantic gamma ray emitting structures extending above and below our Milky Way's disk could be the fossilized imprint of supernova activity from our galaxy's wild youth, when stellar explosions were hundreds of times more frequent. Similar features in distant galaxies observed at look-back times of 10 billion years show how these ancient cataclysms shaped galactic evolution across cosmic epochs. The ultimate frontier lies in detecting true first-generation supernova remnants, those from the very first stars ever to exist. Current models suggest these population 3 stars would have left distinct chemical signatures unlike any subsequent stellar generations. As telescopes push deeper into the infrared, we may soon find stars or gas clouds bearing the unmistakable elemental stamp of explosions that illuminated the universe when it was less than 1% of its current age. These would be the ultimate cosmic relics, carrying whispers from an era before galaxies as we know them existed, when the first stellar death seeded the universe with the heavy elements that would eventually form planets and life itself. When a star explodes as a supernova, the brightest flash isn't the only signal racing across the universe. Hidden within that brilliant burst are trillions upon trillions of ghostly subatomic particles called neutrinos, invisible messengers that carry secrets about the explosion's inner workings. These elusive particles might not light up telescopes, but they're the first witnesses to a star's collapse, often escaping the supernova's core hours before the visible explosion even begins. Picture the star's core as a pressure cooker reaching critical levels. Neutrinos are the steam venting through the cracks, carrying away 99% of the explosion's total energy, while photons, the particles we see as light, are still struggling to escape the chaos. What makes neutrinos so valuable to astronomers isn't just their abundance. About 10 octillion are released in a typical supernova, but their ability to travel undisturbed across cosmic distances. Unlike light, which gets absorbed or scattered by interstellar dust, neutrinos pass through nearly everything in their path. A neutrino produced in a supernova 12 billion light-years away could streak through planets, gas clouds, and even entire galaxies without slowing down, arriving at Earth as a pristine fingerprint of the explosion's initial moments. This means that while we observe distant supernovas visually billions of years after they occur, neutrino detectors could theoretically capture signals from those same events in near real time, offering 2 completely independent windows into the same cosmic catastrophe. Scientists first confirmed this neutrino connection during supernova 1987A, when detectors buried deep underground, like Japan's Kamiok, and registered 24 neutrinos hours before the visible light reached Earth. These faint signals matched theoretical predictions perfectly, proving that core collapse supernovas emit neutrino bursts as their central neutron star forms. Today, upgraded detectors like Supercomputer and an ice cube in Antarctica continually scan for similar pulses from distant stellar deaths. While they haven't caught another galactic supernova yet, these instruments have become cosmic eavesdroppers, waiting to capture whispers from explosions halfway across the observable universe. The information encoded in these ghostly particles is astonishingly detailed. Neutrinos come in three flavors: electron, muon, and tau, that oscillate between forms as they travel. By measuring the ratios of these flavors from a supernova, physicists can map conditions in the exploding star's core with precision impossible using light alone. The particles' energies reveal the newborn neutron star's temperature, while tiny timing differences between their arrivals hint at asymmetries in the explosion, clues about whether the collapse produced a messy, off-center detonation or a clean spherical blast. Some models even suggest that the peculiar anti-kick motions observed in some neutron stars, where they rocket away slower than expected, might be explained by neutrino emissions preferentially carrying momentum in certain directions. Ultra-distant supernovas add another layer of intrigue. As neutrinos traverse the expanding universe, their oscillations could be subtly influenced by phenomena like dark matter or space-time curvature. Hypothetical sterile neutrinos, a fourth flavor that doesn't interact with normal matter at all, might make their presence known by altering the flavor mix over billions of light years. Catching neutrinos from a supernova at redshift 3, when the universe was just 2 billion years old, could test whether particle physics constants have remained unchanged across cosmic time, or if the early universe played by slightly different quantum rules. The hunt for these cosmic ghost particles is pushing detector technology to its limits. Future projects like the Deep Underground Neutrino Experiment will use liquid argon tanks the size of apartment buildings to catch neutrino interactions with unprecedented clarity. Others propose using the Mediterranean as a detector, instrumenting cubic kilometers of seawater to spot the eerie blue glow created when neutrinos collide with water molecules. Every improvement increases our chances of catching neutrinos not just from our galactic neighborhood, but from supernovas so distant their light will never reach us. What began as a curiosity of particle physics has become one of astrophysics' most powerful cross-disciplinary tools. Neutrinos and light form complementary narratives, one describing a supernova's hidden heart, the other its radiant aftermath. Together, they're rewriting our understanding of stellar deaths, proving that sometimes the most revealing cosmic signals aren't the ones we see, but the ones we must learn to listen for in the subatomic static of the universe. Astrophysics has an intriguing puzzle on its hands. Where are all the distant supernovas we should be seeing? Based on our current understanding of star formation rates and stellar life cycles, models predict far more explosions in the early universe than telescopes have actually detected. This discrepancy isn't just a minor accounting error. It hints that something fundamental might be missing from our theories about how stars lived and died when the cosmos was young. One leading explanation involves the very first generation of stars, so-called population 3 stars, thought to have formed from nothing but hydrogen and helium. Without heavier elements to help cool collapsing gas clouds, these pioneers may have grown to incredible sizes, hundreds of times more massive than our Sun. When such behemoths died, they might have collapsed directly into black holes with little visible explosion, leaving no traditional supernova remnant behind. Telescopes like JWST are now hunting for the chemical fingerprints these failed supernovas would have left in ancient gas clouds, subtle traces of ionized helium or unusual element ratios that could confirm this stealthy departure theory. Another possibility lies in dust, not the household variety, but vast cosmic clouds of carbon and silicon particles. The early universe's extreme star-forming environments likely produced tremendous amounts of this interstellar grit, which could be obscuring our view. Imagine trying to spot a flashlight through thick fog. Even the brightest supernovas might appear faint or invisible if their light must pass through dense dust lanes before reaching us. Supporting this idea, some distant galaxies observed by ALMA show dust masses 1,000 times greater than the Milky Way's, creating natural light-blocking curtains around potential explosions. The plot thickens when we consider how these early supernovas might differ from modern counterparts. Stars born in the metal-poor early universe could have exploded with unusual light curves peaking outside the wavelength ranges our telescopes typically monitor or fading too quickly for current survey cadences. There's also the time dilation effect. The expansion of space stretches out distant supernovas' light curves, making week-long events appear to unfold over months. If we're not looking at the right timescales, we might miss crucial phases of these ancient explosions entirely. This missing supernova problem isn't just academic, it has real consequences for measuring cosmic expansion. Type 1 supernovas serve as critical distance markers, but if their early universe counterparts behave differently, our dark energy calculations could be skewed. Some theorists speculate that the missing explosions might represent an entirely new class of supernovas powered by unfamiliar physics. Perhaps collisions between stars in densely packed primordial clusters or exotic magnetic-driven explosions from rapidly spinning protostars. The solution may require rethinking how we search. Current surveys often look for the characteristic rise and fall brightness patterns of nearby supernovas, but ancient versions might exhibit different signatures. Upcoming missions like the Vera Rubin Observatory will scan the sky with unprecedented speed and sensitivity, while JWST infrared eyes pierce through dust to spot obscured events. There's also growing interest in multi-messenger astronomy, combining light with neutrino or gravitational wave data to catch explosions that conventional methods miss. What makes this cosmic detective story so compelling is its high stakes. Every undetected supernova represents lost information about how the early universe transitioned from simplicity to complexity. The elements those explosions forged, the galactic shocks they triggered, and the energy they injected into the cosmic web all shaped the universe we see today. Solving this mystery could rewrite chapters of stellar evolution while revealing whether our most distant cosmic landmarks, those standard candle supernovas, are truly as consistent across time as we've assumed. Until then, the missing supernovas remain both a challenge to our models and an invitation to look deeper, pushing observational technology to new limits in pursuit of the universe's hidden fireworks. Picture this: somewhere in a galaxy 1 billion light-years away, an alien astronomer might be pointing their equivalent of a telescope at the exact same supernova we're observing right now. But here's the twist: they're not seeing the explosion as it appears today. Instead, they're witnessing light that left the star at a completely different moment in cosmic history. This bizarre scenario isn't science fiction, it's the inevitable consequence of how light travels through an expanding universe where distances stretch beyond comprehension. Let's break down how this cosmic timing works. When we observe a supernova 10 billion light-years distant, we're seeing light that departed when the universe was young. But consider a hypothetical civilization located 20 billion light-years from that same explosion in the opposite direction. Due to the universe's expansion, their view would be dramatically different. While we see the supernova as it looked 10 billion years ago, they might observe it as it appeared 15 billion years in the past, or perhaps not at all if the expansion carried the light beyond their visible horizon. The exact timing difference depends on their relative positions in this ever-stretching cosmic fabric. This leads to fascinating possibilities. A particularly advanced civilization might have watched the supernova's entire life cycle unfold already, from the initial shock breakout to remnant formation, while we're still waiting for those light waves to reach us. Conversely, they could be preparing their instruments for an explosion we recorded millennia ago. the variables multiply when considering how space itself stretches over time, meaning two observers could receive the same supernova's light separated by billions of years in their respective timelines. The implications extend beyond simple chronology. Different perspectives on the same cosmic event could reveal unique scientific insights. An alien civilization positioned orthogonal to our line of sight might observe asymmetric features in the explosion we'd never detect, or measure different elemental abundances in the debris based on their viewing angle. Their technology could have captured phases of the supernova's evolution that our telescopes missed, like the crucial first milliseconds when the shockwave breaks through the star's surface, simply because their location in space-time gave them an earlier or clearer view. This cosmic relativity affects even our attempts to communicate. If we somehow identified intelligent life near a recently observed supernova, any message we sent about the event would take millions of years to reach them, by which time their own observations would have long since progressed. The very concept of simultaneous observation breaks down across intergalactic distances, creating a universe where every civilization exists in its own unique bubble of cosmic time, watching the same stellar dramas play out on drastically delayed schedules. Perhaps most mind-bending is how this temporal disconnect impacts our search for extraterrestrial intelligence. The supernovas we use as standard candles to measure cosmic expansion, those Type 1 explosions, might have already served as navigational beacons for civilizations that rose and fell billions of years before Earth formed. Our entire cosmological framework could be built atop stellar explosions that other beings witnessed, analyzed, and perhaps even used to map the universe during eras when our solar system was just a cloud of unformed gas. This temporal kaleidoscope also raises profound questions about the universe's uniformity. When we observe ancient supernovas, we assume the physical laws governing them matched ours, but what if distant civilizations watching the same events at different cosmic epochs saw behaviors that challenge our understanding of physics? A supernova observed 5 billion years earlier in universal time might reveal subtle differences in nuclear fusion rates or neutrino interactions, hinting that fundamental constants aren't quite as constant as we believe. Ultimately, this thought experiment reveals a humbling truth: every observation we make is just a single frame in a cosmic film reel spanning billions of years. The light arriving at our telescopes today carries stories not just about dying stars, but about the infinite perspectives that could exist across the expanse of space and time. So the next time you marvel at a distant supernova, remember, you might be sharing that moment with alien astronomers, just not quite in the way you'd expect. Every supernova we observe, no matter how brilliant or distant, is caught in a race against the universe's relentless expansion. Those ancient explosions whose light has traveled 12 billion years to reach our telescopes face a sobering future. As space continues stretching at an accelerating rate, their light will eventually stretch too far, reddening into oblivion. Imagine the most distant supernova we've detected, DS16C2NM, currently visible only because gravitational lensing magnified its fading glow. In a trillion years, even such magnified explosions will disappear entirely from Earth's night sky, their wavelengths stretched beyond any detectable frequency by the inexorable pull of dark energy. This cosmic vanishing act unfolds in stages. First, the supernova's light reddens as space expands, shifting from visible blue and yellow into infrared, already the fate of most ultra-distant supernovas observed by JWST. Next, the photons stretch into millimeter waves, then radio frequencies, each transition making them harder to distinguish from the cosmic microwave background. Finally, the wavelengths become so elongated that they blend seamlessly into the fabric of expanding space itself. What began as a dazzling stellar explosion ends as undetectable ripples in spacetime, leaving behind only the heavy elements it forged, silent testimony to a death no future civilization will witness. The timescales involved boggle the mind. while nearby supernovas like Kepler's star of 1572 will remain visible for millennia. The most distant examples have expiration dates measured in cosmic terms. A supernova whose light took 12 billion years to reach us today might become unobservable in just another 20 billion years, a blink in the universe's potentially infinite timeline. Future astronomers in our own Milky Way, should any still exist, will peer into an increasingly empty cosmos where galaxies beyond our local group have redshifted into nothingness, taking their stellar explosions with them. Yet these fading beacons leave behind profound legacies. The iron in our blood, the calcium in our bones, all were forged in supernovas that vanished long before Earth formed. Even as the light fades, the chemical fingerprints remain, woven into subsequent generations of stars and planets. The universe won't forget these explosions even when their photons are gone. Their elements will continue recycling through new stars, worlds, and perhaps even life forms in eras we can scarcely imagine. There's poetic symmetry in this grand disappearance. The first stars ignited when the universe was opaque. Their deaths helped clear the cosmic fog. Now, as accelerating expansion renders their final flashes invisible, we're granted a privileged moment in cosmic history, able to look back and see the full life cycle of stellar existence from fiery birth to silent departure. Future epochs may know supernovas only as theoretical constructs or ancient elemental patterns, never witnessing their brilliance firsthand. That makes our current era uniquely special, a golden age of cosmic visibility where the universe's most violent and beautiful moments are still there for us to see if we know where to look. From the violent deaths of massive stars to the echoes of explosions older than our solar system, these 30 facts reveal how distant supernovas serve as cosmic time machines, each flash of light a coded message from the universe's deepest past. We've seen how these stellar explosions forge the very elements that make up our world, how their light bends through space to reveal invisible dark matter, and how they act as celestial yardsticks measuring the expansion of the cosmos itself. They're not just spectacular events, they're forensic evidence helping us reconstruct the history of everything, from the first stars that ignited after the Big Bang to the mysterious dark energy that's pulling the universe apart. What began as flickers of light in ancient galaxies has transformed our understanding of reality. Those faint points of light captured by Hubble and JWST carry revolutionary secrets, proof that the universe's expansion is accelerating, clues about how galaxies assembled their heavy elements, and even hints about whether the fundamental laws of physics have changed over billions of years. Every distant supernova is like finding a single page from a lost cosmic library, each one adding another paragraph to the story of how we got here. The iron in your blood, the gold in your jewelry, the calcium in your bones, all were forged in these cataclysms and scattered across space long before Earth existed. This journey through cosmic time leaves us with an exhilarating thought. Right now, as you look up at the night sky, light from undiscovered supernovas is racing toward Earth. Somewhere out there, a star has already died in a spectacular explosion. We just haven't seen it yet. The next revolutionary discovery about our universe might already be on its way, a photon stream carrying answers to questions we haven't even thought to ask. So here's your call to action the next clear night. Step outside and glance upward. That vast darkness isn't empty, it's a time capsule waiting to be read, a puzzle with pieces stretching back to the dawn of time. Whether you track supernovas with a backyard telescope or simply marvel at the stars with naked eyes, remember, you're part of this story too, built from stardust and living in a universe that's still revealing its secrets one explosion at a time. The cosmos invites us all to keep watching, keep wondering, and stay forever curious about the brilliant darkness above.